This video has two main points. First, we're going to describe the logic of the related samples t-test, and then we'll illustrate the related samples t-test with a full example. So here's the logic of the related samples t-test. You have a population, and you don't need to know the population parameters. But as in most situations, you can't measure the entire population, so you do have to take a sample. What makes this different is before you do anything to the sample, you measure their mean on the dependent variable before you do anything. So if I'm measuring some kind of treatment, I find what their score is on some dependent measure for that treatment before I do anything. Then I treat everyone, and then I measure everyone again. And so I'm literally comparing the same group of people to themselves. I'm measuring them before and I'm measuring them after. Now, if the treatment does not work at all, what should be the case for the mean before and the mean after? If the treatment doesn't work at all, those two means should be the same. Another way of saying that is that the mean difference would be 0. And that's really important that you think about this related samples t-test as measuring the mean difference. That's what this thing is interested in. It's really not interested in the raw scores. It's interested in the mean difference before versus after. What's the difference between the mean before and the mean after? As long as you remember that, you're a long way home. Okay, in this example, we're just going to ask a simple generic question. Does the treatment change scores using an alpha value of 0.05? So since I've said change, does it change scores? I'm interested in knowing whether it increases or decreases, so that means I need to do a two-tailed test. Here are the data before and the data after. And the first thing you should do is compute the difference scores. So the first row of data is a person. Let's say that's Bob. So Bob scored 5 before and 7 after. And we find the difference for Bob to be 2. As long as we subtract after minus before. It doesn't really matter which way you subtract. You could do before minus after or after minus before. In this case, I chose to do after minus before. You just have to make sure that you do it the same way for every individual. So the second row of data is a second person. That person's difference was 1, and so on. You can go down and see how we did that for each person. Now we'll start walking through the hypothesis test. As you state the null hypothesis, it's the mean difference if I put everyone through and measured them before, gave them a treatment, and measured them after. If the null hypothesis is true, the mean difference for the entire population would be 0. Now I do it for the research hypothesis, and now the research hypothesis says the other outcome. The mean difference would not be equal to 0. There would be some change. The treatment is going to have some effect. The next step is to find the critical region. You do that by using the degrees of freedom formula for the related samples t-test, which is n minus 1. Now n in this case is the number of paired scores. So if you look back at our data, we have 1, 2, 3, 4, 5 pairs of data. So n is 5 in this case. So 5 minus 1 is 4. That's our DF. Now we go to the appendix in the back and we find the critical value for a two-tailed t-test with 4 degrees of freedom, and we find that our two critical values are plus and minus 2.7764. And of course, here's a picture of that. So if we get anything in this region, we're going to reject. If we get anything in this region, we're also going to reject. If we get something up here, we're going to say that the treatment increased scores. And if we get something down here, we're going to say the treatment decreased scores. Now the next step is to compute the actual statistic. Now there's a number of steps we have to go through for this statistic. Here is the equation we're eventually going to want to end up using. It's the mean difference, that's what the m sub d is, divided by the standard error of the mean. All of this on the bottom is the standard error of the mean. That's the standard deviation of the difference scores divided by the square root of n. So we need to find all of these different terms. First, let's find the mean difference. We can find this in a couple different ways, but an easy way is to sum up the difference scores. So if we were to add up 2, 1, 1, 2, and 1, sum those up, and then divide by n, which was 5, we would find 7 divided by 5, which gives us a mean difference of 1.4. The next step we want to do is we want to find the standard deviation of the difference scores. Again, what we're using is we want to find the standard deviation of these numbers right here. And to do that, you can see in this equation, we need this term right here, the sum of squares of the difference. Here's the equation for that. It's the sum of the difference scores squared divided by the sum of the difference scores parentheses squared divided by n. Now, where do we find these numbers? Well, we know what the sum of d is, the number that goes right here. We already found that. That's 7. N is 5. So what we need is the sum of d squared. Sum of d squared is found the same way we found the sum of x squared. You need to sum each of the differences first. That's what I've done here. So d squared for Bob, the first person, is 2 squared, or 4. The next person is 1, 1, 4, and 1. If you add those up, you're going to get the sum of d squared, which is going to be 11. So now we have what we need to sub into the sum of squares equation. 11 minus 7 squared divided by 5 is going to be 49 divided by 5. And then subtract that number from 11, and you'll get 1.2. That is the sum of squares of the difference scores. Now we take that number and plug it into the standard deviation of the difference scores equation. And we get the standard deviation of 0.548. That's the standard deviation of the difference scores. So now we need to take that number and plug it back over in here into the t-test equation. So let's substitute in the numbers we have. Again, the mean difference was 1.4. We got that from finding the average of these difference scores. The standard deviation of the difference scores goes right there. And we got that from all of this stuff over here. And n, we of course know because we have 5 pairs of scores. If we crunch those numbers, we're going to get an obtained t value of 5.71. That is found right in there on the curve. It is in the critical region, which means we are going to reject the null. It's in the top critical region, which means that we increased scores. The next step is to compute the effect size. We do that with this equation. And we substitute the numbers from the previous screen, and we find the effect size is 2.55, which is very large, telling us that the effectiveness of the treatment is very large. And now we need to summarize the results in an APA format. Scores after the treatment were higher than scores before the treatment. And then I have stat stuff, and then a summary statement about the effect size interpretation. The large effect size suggests that the treatment was very effective. The same format in this reporting statement as we've been using for quite some time. The first sentence is just telling us whether the outcome of this hypothesis test was likely or unlikely to be influenced by sampling error. The difference between the before and after means, in this case, was unlikely to be caused by sampling error. The difference between 7 and 5.6 was so large that it was unlikely to be due to sampling error. And so what we say is that the two scores are different. T, because we ran a t-test, 4 because that's our degrees of freedom, 5.71 is our obtained t value. The p is less than 0.05 because rejected, and then here is our d. And you always put a period after the d. If you use it at the end of the sentence, that is, which is the typical format. And then we have the second sentence, which is just an interpretation. What you want to help the readers interpret what the results mean.